Your next homework assignment having to do with pumps is posted on Blackboard right now, and it's going to be due on Tuesday, the 22nd of February, so that's due by 1 p.m. And then the reason for that is that day at 1 is when the solution will become available, and you'll have 24 hours to look at the solution before we have our exam on Wednesday, February 23rd. I'll talk more about the midterm exam on Friday, just to give you an idea of how to begin preparing for that. But it's going to include all of the lecture material up to and including Monday of next week. Today we're going to continue talking about pumps. Any schedule or announcement questions before we begin? All right. On Monday, we talked about how you find the operating point when you've got a pump operating in a system curve. In a system. I gave it away. I was going to ask you, how do you solve for the operating point? Like, what's the calculation process? And the answer is you set the system curve equal to the pump curve, and you solve for Q, the flow rate. And so both the system, which is the energy equation rearranged in terms of H sub P, the system can be represented in terms of H sub P, and that's how the pump is also expressed as a function of pump head added and flow rate. So on the homework that I've just loaded onto Blackboard, one of the problems that you have gives you a pump curve in graphical form rather than as an equation. And I think this is good practice to digitize a curve. The pump curve follows what we typically see, which is that you have a high flow rate when the total head that it's being added is low, but then as the head that has to be added increases, the flow rate goes down. And so there's this curve, but you can't put this curve into an equation, not directly. You have to find an equation out of it before you can set it equal to the system curve. So the system curve is given in the statement, but you're having to create the pump curve. And this is the format that pump curves typically take. And so the y-intercept is H sub P, and H sub P, the pump head, is what you're calculating. There's some cutoff head. Here you can see that's 200 feet is the y-intercept. And then the pump head added decreases as the flow rate goes up. And so the parameter C, this coefficient that goes in front of the flow rate, is what you're going to have to determine by digitizing the curve and trying to solve for the lowest guess value of C. And so you can set this up on Excel and pretty quickly and easily determine what coefficient should be used by minimizing the average difference between your observed curve and the guess value of the pump head based on some factor of C. So for example, when the flow rate is 0, the pump head is 200. When the flow rate is 20 CFS, so here at 20 CFS, then you can see I'm estimating that it's about 150 feet of pump head. And so when it's 10 CFS, then it looks like it's probably about 180. So what you should do is for 5, 10, 15, 20, 25, 30, 35, for all of these values, determine the flow rate and the head. And so fill in this figure, this 2 columns of data from the figure, and then try and predict the pump head using this form of the equation with some guess C value that you have at the top. So in the spreadsheet, let me just copy this whole thing over to Excel to give you an idea of what I mean. So here is C, and I don't know what C is. Let's say maybe it's 1. All right, and then the form of the equation is this. Let me just paste this so that it's available for us to look at. So if C is 1 and y-intercept is 200, okay, if that's the case, then h sub p would be the y-intercept minus c times q squared. All right, so far so good. The difference between the known pump head and this calculated pump head is 0. So the difference between known and calculated. So there's no difference. But then for this next one, at a flow rate of 20 CFS, then it would give us minus 200 as our guess pump head. But what we know, the actual pump head is 150. And so the known minus the difference here is 350. So it looks as though maybe 1 isn't a very good guess for the C value. What if I said 0.5? Well, that's pretty good, because look, the calculated, we're headed in the right direction anyway. The difference between the known pump head and the calculated is smaller. What about 0.4? All right, that's getting better. 0.3, getting better. So I could do the same thing here. If I had 10 CFS, let's go back to the figure. If it's 10 CFS, then it looks like the total head, I'd want to get out like a ruler and really be precise about this if I was doing it as a homework problem. But let's just say it's 185. Okay, so 185. Okay, so if that's what we observe, then what would be predicted if this is our C value? Okay, so the predicted is it's the y-intercept minus C times q squared. All right, so then the difference between the two. All right, so I do this for lots of different flow rates, 5, 10, 15, 20, and so on. And then I have this average difference. What I want to do is I want to find what is the C value that gives me the smallest average difference. So then that will give me confidence that the C value I've determined is the one that actually traces this curve best. So you're given a curve, but what you need is an equation, because remember the problem-solving process here is h sub p with the system curve should be set equal to the h sub p of the pump curve, and you just don't have the pump curve in numerical form. You've got the pump curve in graphical form. So that's just a little bit of a hint, and I think on the handout it kind of explains as well that what you're trying to do is minimize the difference between the known and calculated h sub p by trying to get just the right C value. So is it 0.25? That made the C value, that made the average difference a little bit smaller. And of course, our objective is to have the smallest possible difference. And so if you have the solver on your computer, then our goal is that this should be minimum. I don't think we'll get necessarily the difference down to 0, but we want to minimize that by changing the C value. So the C value can be adjusted. So this is not enough data points for us to get a reliable C value with just 3, but that's the process that you should follow. We're trying to find the coefficient. So hopefully that helps to explain it. It's just another numerical technique and what you need to be able to do to find out when you use this pump with this system, what's the operating point. So I guess another approach is that you could graph the system curve on the same figure. You know, if you graph the system curve and you find where's the point of intersection between the pump curve and the system curve, that's the operating point. Remember from this figure, the operating point is where the system curve and the pump curve go together. So you've already got the pump curve, and you've got an equation for the system curve. So where do the two come together? That's the kind of the essence of problem 4. All right. This is what pump curves really look like when they're provided by manufacturers. They have a lot of different information on the same figure. And you'll see some of the things that we're already acquainted with. So the typical shape that I've showed you so far is this, where there's a cutoff head, and then the head is decreasing as the flow rate goes up. And we do have that on here. Look at this particular pump. If it's operated at 3,600 RPM, would have a cutoff head of about 450 feet. But then as the flow rate increases, then the head it's able to offer goes down. And this is the same pump. If instead of being spun at 3,600 RPM, if you spin that pump with a motor that goes 3,200 RPM, then it only has a total cutoff head of about 360 feet. And then declining head can be added as the flow rate goes up. So number one, this is a single pump, but they're showing what if you matched it with different motors that operate at a variety of different speeds, or if you had something called a variable frequency drive that changes the characteristics of the electricity that's going into the motor, and with that changes the RPM that it operates. So one of the things that you can get out of these manufacturer-provided pump curves is just how the pump operates at a variety of different rotational rates. But then there's also curves of efficiency. So here where it's saying 50, 55, 60, these are curves that are expressing the efficiency factor of just the pump. And so it looks like the most efficient operating point for this particular pump is it's going to achieve about 65% efficiency when it's pumping around 400 GPM and adding around 400 feet of head. And so this can give you an idea of the optimal range to operate a pump. And of course, it can add head and it can move water at other rates besides that optimal range. But just from the perspective of energy consumption, it's going to be most efficient when you're operating it here in this zone than outside that envelope. The other thing I wanted to point out is what's called here NPSH. And this NPSH is related to the risk of cavitation. And it's telling you how much, what's your safety factor, how close you're going to be to cavitation at different operating points within the pump, because it requires a certain amount of net positive suction head to prevent cavitation. So let's talk about cavitation risk a bit more. I've already explained to you in previous occasions that on the suction side of a pump, that the pressure is decreasing in the direction of flow, and that if the pressure gets below the vapor pressure of the liquid, that those little vapor bubbles can form at the impeller inside the pump. And those vapor bubbles are dangerous because when they collapse, they send a shock wave through the water that can scour and pit the surface of the metal impeller. So those bubbles collapsing cause really high concentrated pressures that cause a reverberation in the water. So the things that will increase the risk of cavitation would be a long suction head pipe, because the longer the pipe is, the more friction loss is going to take a toll. Or a small diameter suction pipe is going to increase the risk of cavitation, because if the diameter is small, then that means the velocity in the pipe is high and there will be relatively more head loss. And so you're getting closer and closer to the risk of the pressure inside the pipe and inside the pump getting down to the vapor pressure. Here is a picture that shows some pitting on the surface of an impeller that was caused by cavitation. And so it's not rust so much as it is kind kind of a scour effect, that or a tiny explosion in the water that's chipping away at the metal. All right, so net positive suction head is the way that we can measure whether or not there's going to be cavitation. And the available suction head is determined by looking at the system. And so the most suction head that's available is just related to the atmospheric pressure. And so all the other terms in this equation are negative except for the first one. And so the first one is the atmospheric pressure divided by the unit weight of water. And then all the terms after that, the delta Z in the suction side head is just related to the elevation difference between the pump and the water surface. And so the delta Z sub S is the suction side elevation difference. Head loss on the suction side is the combined effects of local and friction losses. And then you also subtract out the vapor pressure of the liquid at a different, at whatever temperature is applicable. So remember that as the water gets warmer, the vapor pressure goes up. So you have more risk of cavitation with warm water than you do with cool water. So here are all those terms defined. And you have to compare how much suction head is available to how much is required by the pump. And that is what comes from these pump tables. And so what this is saying, for example, is that when the pump is operating at a certain point, it requires 6 feet of head minimum, otherwise it will begin to cavitate. So this is a measure of how much suction there is inside of the pump itself. On the suction side of the pump, how much suction there is, and if you have less available net positive suction head, then cavitation will occur. So the process is that you would calculate the available NPSH, compare it to the required NPSH, and then if the required amount is greater than what's available, cavitation occurs. All right. And if the required net positive suction head is equal to what's available, they call that the point of incipient cavitation. That means it's just right on the verge of beginning to cavitate. All right, so just as some practice, let's look at this following scenario where water is being pumped out of a lower reservoir. It's being lifted and discharged to an elevated reservoir. Now, you only measure the elevation difference between the lower tank and the pump, not the elevation difference between the two tanks themselves. So the delta Z is just talking about the elevation difference on the suction side of the pump. So it's from the water surface to the pump itself. And the same thing is true with the head losses. It's just the suction side head losses that you're going to be accounting for. So here in this example, I've told you what the water temperature is, and so from that given water temperature, we could look up the vapor pressure of water, the unit weight of water, and all those things are going to go into the NPSH available. And this particular pump, what we know from the manufacturer is that it has a required NPSH of 3.8 meters. So what you do is calculate the available NPSH and compare it to what's required. And if available is more than required, there's no cavitation. If available is less than required, then there will be cavitation. So let me pause for a second, and you should calculate NPSH available. Okay, so we have to do these in absolute terms. You know, this vapor pressure is given in absolute terms. You'd use the atmospheric pressure in absolute. And at sea level, you're starting off with 101,325 pascals. I suppose if you were going to do this in Leadville, Colorado, where the altitude is above 10,000 feet, then the atmospheric pressure would be even lower, which means there's more risk of cavitation. But here, let's take a look at where things shake out. So we've got the atmospheric pressure divided by the unit weight at the temperature that we know, the suction side losses the elevation difference just between the suction side and the pump, and then subtracting out the vapor pressure term. So our available net positive suction head is 3.76, and since that's greater than what's required, it says here that it's requiring 3.5, then there's not going to be cavitation in this example. But there are some things that could cause it to cavitate. You know, if we had more elevation difference, all we would need to do is lift up this pump another 0.2 of a meter and it's going to cavitate. So if it was a foot higher off of the ground, then it would cavitate. Or if this suction side pipe was a little bit longer, or you know, a rougher pipe material, then that would increase the head losses, and then that would also cause cavitation. Or if it was warmer water, it's potential that that could have been enough to further reduce the amount of available net positive suction head. So all of those things need to be kept in mind when you decide where to place pumps. All right, and just to get a bit more practice, let's take a look at another pump operations example where we have a pump curve that's given, and you're going to have to generate the system curve. And so here in this system, we're lifting water from a lower reservoir, and what we know is the local losses that have to be accounted for is there's a K value with this inlet, and then there's just going to be the friction losses that occur, and then this is being discharged as a jet. So when we put this into the energy equation, of course we can cancel out V1 because it's in a tank, but V2, since it's discharged as a jet, we won't cancel out the velocity head term there. So we can rearrange the pump head in terms of this, but the only other thing to point out is that it retains the velocity head. I think velocity head's usually pretty small, but I guess the way I would rearrange this equation, if we are going to keep the velocity head in play, let me rewrite on the board what the system curve will look like. So the system curve is going to be written in terms of H sub P is equal to, all right, and then we've got the elevation difference, so the delta Z plus Q squared divided by 2GA squared. And so then there's going to be 1 that's from the velocity head plus K, which has to do with the inlet. So that's saying that we've got a K of 1. And then also the friction losses. And so we've already taken out 2GA squared. Then what would be left for the friction losses is just F times L divided by D. Okay, so this is going to be the system curve. Now what's tricky, of course, is the F value, because we don't know the F value until we know what the flow rate is. And we don't know the flow rate yet because we don't know the F value. So our typical approach for that is just to estimate, oh, the F value is given. Oh, that makes things easy, right? Otherwise, you'd use the fully turbulent flow assumption, and you determine the F value based on what the pipe is made out of, the diameter of the pipe. But I guess I just cut straight to the chase for this one. So use an F value of 0.021. All right, so I'm going to pause, give you a chance to substitute in and find out what is the system curve, and then set the system curve equal to the pump curve, and solve for Q. All right, so let's just take a look and see, first of all, if we've got the same system curve. So there's a couple of steps we have to go through. First of all, identifying that the delta Z that applies is 12 meters, finding the cross-sectional area of the pipe. And so the pump head is going to be 12 plus 282.1 Q squared. And if you neglected the velocity head, then that would be a bit lower. But did anybody else have the same system curve of H sub P as 12 plus 282 Q squared? See at least one head shaking yes. When you solve for the operating point, I think what you should get is that the flow rate's going to be 1.44 cubic meters per second, just by setting the pump curve and the system curve equal to each other. So here's that. The pump curve that was given was 18 minus 5.6 Q squared. And then the system curve that we just determined, 12 plus 282.1 Q squared. So what remains on the left-hand side of the equation is 6, and on the right-hand side of the equation, 287.7 Q squared. So that means that the flow rate should be 1.44 cubic meters per second, and so therefore, if you substitute that flow rate back into the pump equation or the system curve equation, then what you'll get is that the pump head that's being added is 17.85 meters. That's how much head has to be added. And if that's the flow rate, then a metric ton of water, the 1 cubic meter, is going to take 6.9 seconds to be pumped. So I'll pause there for a moment and give you some additional time to either copy down those calculations or check your calculations. But there is a part B to this question. The second part is asking if you have a pump efficiency of 0.8 and a motor efficiency of 0.65, then calculate the overall combined efficiency and then determine the amount of power that's going to be going in to the motor, the electrical power. So you can see the relationship between efficiency, the power equation, the ideal power equation, and then the actual power equation. So if we know that the pump head being added, we just calculated the H sub P, the pump head being added is 17.85 meters, and we know the flow rate is 0.144 cubic meters per second, then let's calculate how much power is going to be consumed by the motor in order to get the water to flow at that rate. Okay, so we already know the pump head that's going to be added and the flow rate. So the first step would be to find the ideal power requirement if there was 100% efficiency. And then we'll take into account the efficiency factors. So the combined efficiency factor is 0.52. If you multiply together the motor efficiency of 0.65 and the pump efficiency of 0.8. And then the power equation is where we're multiplying the flow rate by the unit weight of water and the 17.85 meters of head that the pump has to add, and then divide by the efficiency factor. So this is going to require 48.5 kilowatts, and that's really a lot of electricity. That's a huge amount of power, but keep in mind it's lifting this water, it's adding 17 meters of head, and we're talking about 144 liters per second. So it's a high flow rate and it's adding a lot of pump head, so it would make sense that there's going to be a large electrical requirement there, especially because about half of the energy that we put into the system is being lost. Only 52% of it is going into the water. All right, that's all for today. Homework 6 is posted now. It's on Blackboard. You may want to get an early start just so you could figure out how to digitize that curve. I'll see you on Friday.